Great. Because these have real coefficients, the conjugate root theorem says that the conjugate is the other root. So minus 4 minus 3i. B, we write this in polar form. It's in the first quadrant here. It's actually easy to see. It's 1 plus I, which means this is 45 degrees. So you could use tan inverse, but I can see quite clearly that the theta is 45 degrees, and I can also see that if I have 1 and 1 here, that the modulus would be root 2. So this is square root 2 cos 45 plus I sine 45 power 8. De Morgan says the 8 multiplies the angle and goes on this one. That's 16. That's cos 360, which is 1, and that's sine 360, which is 0. So that's just 16. Okay, and then finally C, we're given one root and we want the other root, so just division. Z minus 1 plus I divided into the quadratic z squared plus minus 2 minus I z plus 3 minus I. So to get z to become z squared, we multiply by z. That's z minus 1 plus I times z. Then we have to subtract the 2. Sorry, I just realized I accidentally wrote down here minus I when it's minus 2 plus I. So I have to correct that. Okay, back to the long division. So as I was saying, z times z is z squared, and then z times this guy, there it is there. Then we subtract the 2 lines. Minus 2 minus 1 is minus 1, and then I minus I is 2i, and then carry that down. So the next term here has to be minus 1 plus 2i. If I multiply that out, minus 1 plus 2i times z is minus 1 plus 2i times z, and then hopefully when I multiply this by this, hopefully I should get minus 3, plus 3 minus I. That's what hopefully I should get when this guy multiplies this guy. It should make this here, because I want everything to cancel when I subtract them. So the other root would be 1 minus 2i, but what I should do here is just check that multiplication works. So minus 1 plus 2i times minus 1 minus I. So minus 1 is 1, minus 1 minus I is I, minus 2i squared. So that's plus 2, so that's 3 minus I. Yeah, so it works, and we have the second root, and it's correct because the remainder is 0.